All right, welcome back. And here we are doing a couple of practice questions. I have two practice questions that we're going to cover in the same video. This first one is just allowing us to figure out which of these statements is true. And we're basing it on f of n being n squared times log base 3 of n and g of n being n squared. So we haven't actually covered the definitions of each of these, which we will soon. But you'll basically trust me for now in what those mean when you're going through these. So for big O, which is A here, we're basically trying to ensure that n squared log base 3 of n is less than or equal to m times n squared, where I get to pick that m. I get to pick that m, and we also get to pick the n naught for all n greater than the n naught. So we look at this one here, and we can see that basically that would mean that m would need to somehow relate to this log base 3 of n. And the problem is, because in the definition of big O, m is declared first, it's impossible for us to frame m in terms of n. This means that we'll pick a value of m, and then we're going to pick the value of n to be infinity, and this entire statement will be rendered false. So it's important to remember that definition, to recognize the order of terms is going to really affect this overall. So since we can't guarantee that the m we chose will be greater than or equal to log base 3 of n, we have to say that this is not a true statement. Now, when we want to go and look at the next one, we can say n squared log base 3 of n is going to be greater than or equal to m times n squared. And again, we can ask ourselves the same question. Here, we're looking at this m here, this here. This is supposed to be a squared. Sorry about that. N squared. But now, again, we're going to pick a value of m, and we're going to pick it right away. So it doesn't matter. Let m equal 5. It doesn't matter, right? We're letting m exist. And the question is, for all n greater than n naught, would we be able to prove that this holds true? And what we'll find is we can, because we'll have first picked our m, and then as n continues to grow, we will see that this whole side will always grow faster than this, regardless of what value of m you end up picking there. And so recognizing that is the key to realizing that we are in big omega of g. Next, when we look at big theta, or just theta, I suppose, we're basically binding our function by two different sides. Whoops. So we want to make sure that m1, that there exists an m1 times g of n, which in this case, I guess, is n squared. N squared. This needs to be less than or equal to n squared log base 3 of n. And we want to bind it on the other side as well, where n log base 3 of n needs to be less than or equal to a different multiple of that same g of n. And what we'll find is, basically, for this to be true and for this to be true, both of these needed to be true. So since they're not both true, one of these two sides is false. If we look close enough, we can see that this side was true, but this side was false. False and true is going to result in a false. So this can't possibly be one of our true statements. All right. Next, we're going to look at little o. And again, we're going to talk more about it later, but effectively, we're saying for all values of m greater than 0, there needs to exist an n naught greater than 0, where for all n greater than n naught, our statement holds true, less than or equal to m times g of n. Now, basically what this is saying is for all m, so for all multiples of g of n, this needs to hold true in order for us to potentially look at this in a way that makes it a little bit easier for us to fathom. This is effectively analogous to f of n is strictly less than g of n. It means that we can completely ignore the multiples, and we want to make sure that we're still finding a value that's less than n, multiple of g of n. So what this is saying is a strict upper bound. So big O was actually a slightly looser upper bound over this one. This is saying that it doesn't matter how you transform that graph. It doesn't matter how many multiples of g of n you potentially have. This is still going to be an upper bound, even with a million, even if there's a million of them, and even if there's only one of them, we're still going to fall below that upper bound. So keeping that in mind, we're going to write out what this one should look like, and we're going to use that analogous statement. So we're just going to say n squared log base 3 of n is strictly less than n squared. So unless they were equal up here in part A, which they weren't, this one is also going to be false, right? If it wasn't less than or equal, then it's, pardon me, it's not going to be strictly less than, because this is our tighter bound. So this one can't possibly be true. The last one we want to look at here is follows the same suit as little o, but it's little omega. So for this one, the sign is just flipped. So we end up with n squared log base 3 of n being strictly greater than n squared. Now, again, if it was true here, it is in theory possible that this was very specifically reliant on a value of m, and we are not allowed to rely on a value of m in this scenario. So that would require us to actually like potentially take the time to sit down and prove it correctly. Like if we weren't quite sure what was going on, that's something that we can find just by proving it. However, because of the way that like a strict bound works over a less strict bound, with this, whoops. With, there we go. Oh gosh, I keep losing this line here. Sorry, that's just gonna drive me crazy. What we can see here is that this does also rely on n. This term right here does rely on n, so this whole term will grow at a factor of n that will be faster than this factor of n alone. And so we can see that yes, E also is indeed a correct answer. So we have B and E as both being correct answers here. Now we're going to look at one more practice question before we close out this video and move on to some theta, little o, and big O exercises. All right, so here we have another one where we have f of n plus 2 to the n, and we're trying to figure out which of the following statements are true. Now, a reminder about that hierarchy where we had like log n is less than n is less than n squared is less than n cubed is less than 2 to the n is less than 3 to the n is less than n factorial, etc., whatever it was. So we can see how this will start to all come together here, because it's important for us to remember this hierarchy of functions so that we can accurately determine how to classify our algorithms. So imagine that we have this function here, n squared plus 2 to the n, and we're trying to determine right here if it's in little o of n squared. So the question we're asking ourselves here is it strictly less than n squared? That's effectively what we want to ask ourselves. Now, this is very different than the previous one. I will just scroll back up for a second, because a reminder when we looked at this one here, where it was true, because this was a factor of n right here, we knew that that this factor is indeed dependent on our value there. And same thing over here, right? We knew that this wasn't going to be strictly less than because of this extra term right here. Oops, that's too far. This extra term right here, it definitely couldn't be strictly less than. And so then using that logic, we're going to come and look at this one, and we see that n squared plus 2 to the n is not going to be less than n squared. For one reason, because this term is so much bigger, right? But also because we do have that extra n term that we have to consider. So we can tell that this just isn't going to be true. Now, the next one they want us to consider is if n squared plus 2 to the n is in n to the 4. And by the same logic as previous, we can see that if it wasn't in n to the squared, but for the same reasons, it's not in n to the 4. We have this extra term here. We have this extra term here that's causing us problems. So this also can't possibly be true. Now here's the one where we're going to really see what the difference is with that strictly less than. So right here we have n squared plus 2 to the n strictly less than 2 to the n. Now, if this was a big O, we would be able to pick an m value right here where this could be true. We could pick a big enough m that we could essentially equate them, that they could end up being the same potentially. However, because this needs to be true for all values of m, no matter how small m is, no matter how large m is, it does not matter. We have this strictly less than, pardon me, we can't say that this is true because n squared plus this 2n is not strictly less than the 2 to the n alone. Like that's just straight up not true. So this is going to be false. Whereas if it was in big O of 2 to the n, you would be able to prove potentially that something different. So next, let's look at 3 to the n here. So we have n squared plus 2 to the n is going to be strictly less than 3 to the n. And of course, we can use the roundup trick very simply to prove that we could pick an n naught that would force us to be above a value where this would be true. So we can use the roundup trick to prove that it is strictly less than 3 to the n. So this one here is true. And then again, so we saw that here in that hierarchy of functions, but we can also now for this one do the same thing and see that 2 to the n is definitely going to be strictly less than n factorial. And we really are just trying to determine how quickly these are growing in relation to each other. And this is indeed going to be strictly less than n factorial by the same reason. Now we won't see a whole lot of problems that live in this space here. Like in that exponential space and higher, we just don't see very many of them because there are no solutions to problems that, like good solutions to problems, I should say, that would have a running time like that. But we will see lots of them that fit in the polynomial space instead. All right, so those are our 2 warm-up questions with respect to big O, little omega, and theta. In the next video, we are going to take another look at a couple of additional proofs in the next few videos concerning ourselves with theta, little o, and little omega. All right, thanks so much for joining me, and I'll see you in the next video.